Thank you. So, please welcome Jean-Philippe Amazon, DJ Bernstein, and Martin Boslett, which you may know from 28C3, where they showed that several common web application programming languages were vulnerable to hash flooding attacks. And now I believe you will hear much more and in deeper stuff about the subject.
All right, thanks. Actually, so from 28C3, it was Klink and Velde. I'll get to that in just a moment. Let's start by rewinding a little flashback to 1998 from Frack, where Solar Designer had an article on designing and attacking port scan detection tools. And there's some great passage here, which I'd just like to quote to you. So you can read along if you like. In scanlogd, this was this utility that he wrote for checking for port scans. In scanlogd, I'm using a hash table to look up source addresses. This works very well for the typical case. Average lookup time for this hash table is better than a binary search. However, an attacker can choose her addresses. This might be one of the first female attackers that we've seen. It can choose her addresses, most likely spoofed, to cause hash collisions, effectively replacing the hash table lookup with a linear search. Depending on how many entries we keep, this might make scanlogd not be able to pick new packets up in time. I've solved this problem by limiting the number of hash collisions and discarding the oldest entry with the same hash value when the limit is reached. Okay, problem solved. This is acceptable for port scans, this limiting the hash number of hash collisions. Remember, we can't detect all scans anyway, but might not be acceptable for detecting other attacks. It's probably worth mentioning that similar issues also apply to things like operating system kernels. For example, hash tables are widely used there for looking up active connections, listening ports, etc. There are usually other limits which make these not really dangerous, but more research might be needed. Kind of prophetic. So, all right, let's rewind just a little bit more. So what are these hash tables? I figure most people have used hash tables or are familiar with them, but just to make sure we've got the notation straight here, a hash table is a bunch of linked lists. The number of linked lists you use, let's call it L, and let's just assume L is a power of 2, so maybe you have 256 or 1048576 linked lists in your hash table. L separate linked lists. And what you do with a string to store it in your hash table, of course you can store things other than strings, but let's focus on strings, one of the most common uses of hash tables. You put string S in list number I, where that index I is going to be some hash, that H there is some hash function you choose, hash of the string modulo L. So you compute some hash and you reduce it mod, say, 256 if there's 256 lists in your table, and that's the position of the linked list that stores your string. If you've got, say, n entries in your table and there's L positions, L different linked lists, then, well, your average linked list is going to have n over L entries. And so you figure most of the entries are going to be about n over L, maybe a little shorter, maybe a little longer. The entries are the lists. Most of the lists will have about n over L strings stored inside them. And if you choose your L to be sized appropriately for the number of strings you're going to store, then say L and n are about the same size, then you're going to have about 1 or maybe 2 or 3 entries in each linked list. Now let's look at a picture of what you could do here. If you just choose your hash function to take the first byte of a string, let's try storing the strings 1, 2, 3, I mean the ASCII strings ONE and TWO and so on, 10 strings in a hash table of size 256. Should be big enough for storing 10 strings. Well, there's an array of 256 linked lists, array of 256 pointers, where the T pointer, for example, at the bottom, the T is pointing to the string TWO, which is pointing to the string THREE, which is pointing to the string TEN. So there's actually quite a pileup of strings on the T. There's 3 different strings, 2, 3, 10. These strings all hash to T because the hash is just take the first byte of the string. So there's not a good distribution of these strings across the hash table. This is not a good hash function, just taking the first byte of a string. Some applications, practically every string that you hash has some fixed first byte, and then you're going to have all of those strings piling up on a certain linked list. No matter how many linked lists you have, if you've got some hash function which does a bad job of distributing your strings, strings through the linked list, then you're not going to get good performance. Linked lists are slow. Hash tables are supposed to be fast by making the linked lists short. Short linked lists are fast, but that doesn't work if your linked lists get long. So in an application where you've got a lot of strings with the same hash value, for instance, for this hash function, you've got a lot of strings which have the same first byte, your performance is horrible. So what do? Well, you somehow look at the whole string, and you somehow compute an index modulo L from looking at the entire string instead of just, say, the first byte or the last byte or something that might be completely predictable for your application. And this is something where for 60 years people have been working on good hash functions that really quickly look through the whole string. So these functions, it's important for the hashing to be fast so you can quickly process whatever your length of string is that you're storing in the hash table, and it has to give random looking results to spread your strings out across a bunch of different linked lists. And if you don't spread out your strings well, you'll spend a long time looking through a linked list where you have things piling up. As a result of this, programmers exploring lots of different hash functions, we've got good hash functions, and it's textbook material how to make a good hash table which for typical strings gives you good performance. But when you're the attacker, you might not choose to give somebody a typical string. So let's look at hashing malicious strings. And this is exactly what Solar Designer was talking about, where the attacker chooses a bunch of strings which have the same hash value. Now, suppose that all n of the strings going into the hash table have the same hash value. Say they all have hash 0 modulo L. Then they're all going to be in linked list number 0. And so your hash table is doing no good at all spreading things out. It's putting everything into this first linked list. And that linked list has n entries into it. And the time to look through for n strings is going to be n squared. And if n is big, that's really, really slow. So you could try to solve this. You can actually successfully solve this by, instead of using linked lists, instead of having L linked lists, you can have something like L red-black trees, or L something complicated. And then you end up with some sort of balanced tree structure times L different, whatever those structures are. And this will give you guaranteed good performance if you choose a sensible, balanced kind of tree structure. But nobody likes doing this. It's really rare for somebody to implement this kind of thing because it's such a pain. I mean, even doing one tree structure is a pain, and then having to hash it and manage a bunch of those and have whatever number of trees, say L trees, where you have to dynamically adjust L, it's a pain to do. So nobody actually, well, a few people do this, but realistically, most people don't do hash tables that consist of fancy data structures. Hash tables consist of linked lists or something similarly simple. One of the big advantages of hash tables is they're a simple data structure. It's something you can reasonably get right without having a whole lot of iterations of debugging. So people don't like that solution. You could try to do something like what Solar Designer was suggesting for scanlogd if your application is happy with it. So for instance, in my DNS caching software, the cache is the ultimate example of anything you're caching. It doesn't have to always work. The whole point of a cache is that it has to work most of the time in finding something in the cache, but if it doesn't find something in the cache, there's some backup mechanism to retrieve the data that you wanted to get from the cache. So it's okay. It's just one line of code here which says to protect against hash flooding, this attack, just if some counter which was keeping track of how long you've gone through a linked list, if that gets to 100, then don't put anything more on that list. So that limits the number of entries in a list inside the hash table in this cache, limits it to 100 entries, and the performance problem goes away. But if you have a general application of a hash table, if you have an application that's not just doing a cache or some scan that's not expected to always work, if you have an application which needs to store data and retrieve the data later, which is what most hash tables need to do, you cannot do this simple kind of solution. So you need to successfully store all the data that comes in and not just start throwing it away because you think it's going to be a performance problem. You could say, okay, we've got some great hash functions out there that definitely spread your data across a lot of different output values. Like SHA-3. This is the latest and greatest hash function. Use SHA-3 as the hash function, and it's collision resistant. You're not supposed to be able to find any two strings which have the same SHA-3 output. The reason this is a bad solution is that, well, first of all, it's very slow. Like I said, the whole point here is performance. You want your hash function to be fast, and you want it to spread out your strings well so that searching through each linked list is fast. But even if it were fast enough, it would not solve the problem. It doesn't prevent the attacker from having a bunch of H values pile up, because the attacker doesn't need the H outputs to collide, doesn't need to find collisions in SHA-3. The attacker needs to find collisions in SHA-3 mod, say, 2 to the 16, or whatever your L is, whatever your hash table size is. And this SHA-3, no matter how strong it is, you could have the world's most amazing hash function and then reduce it mod 2 to the 20, whatever the size of the hash table is, and suddenly the attacker can find collisions. The attacker just tries a million inputs, and then one of those outputs is going to have a value of 0, say. And then the attacker looks at another million inputs and finds a string whose output, whose hash value mod 2 to the 20 is 0, and keeps doing this, and after a reasonable computation, the attacker's piled up thousands, millions of strings which all have hash value 0, and then feeds all those strings into your application, and the application does the same computation. The hash table puts everything into, does the same H of S mod L, puts everything into linked list 0. Performance disaster. So this is not something which is obviously easily solved, and it's been exploited repeatedly. 2003, Crosby and Wallach had a paper where, well, I guess they thought they were the first to think of it. They said they have this new class of low bandwidth denial of service attacks. Everybody comes up with a new name for these, like hash flooding, hash denial of service, algorithmic complexity attacks. If each element hashes to the same bucket, the hash table will also degenerate to a linked list. And okay, the idea wasn't new, but they had some new examples of these attacks. For instance, they took Perl and said, here's some strings which Perl will always, no matter what application you write in Perl, if you're using Perl's hash tables, then these will all get hashed to the same value. Or the Squid web cache, or they also took an intrusion detection system, just like the 1998 example, and broke that. And now here's the 28C3 result. So Klink and Valda said, efficient denial of service attacks on web application platforms. You can see the list there of some of the things that were admitted to be broken as a result of this. Look up the OCERT advisory if you like. The most common response from these applications was, and also the response that Perl took back in 2003, was to randomize, secretly randomize the hash function. Instead of having a hash function that everybody knows, that the attacker knows and can try finding strings that all hash the same value, have a hash function that is random and secret, so the attacker doesn't know what the hash function is. And then, well, how is the attacker going to figure out strings that collide? You've got your secret hashing, and the attacker doesn't know what your secret is. Well, what we're going to talk about in the rest of this, I'm going to sit down in a few seconds here, the rest of what you're going to hear about is whether this actually works, whether it's actually secure. Okay.
Okay, so I want to present to you an attack that we did, and our target was the murmurhash family of functions. There's murmurhash 2, which is widely used in projects like CRuby, JRuby, the Redis NoSQL database. Then there's murmurhash 3, which is the successor to murmurhash 2, obviously. And interesting fact is that this was introduced in Oracle and OpenJDK last year as a response to Klink and Valda's attack. And the same thing happened in Rubinius, so they used a randomized version of murmurhash 3. So let's talk about the theory of this attack. As my example, I will use murmurhash 2 in a 64-bit version that's being used in CRuby. So this is the gist of the algorithm. You have this constant m up there, which is fixed. This is a magic value. Then there's H, which carries the state of the hash, and it's initialized by the seed and the length of the message to be hashed. And in this while loop, this is where most of the work happens. This is where all the individual message blocks will be processed. So what you immediately notice there is that the seed is only used once right there at the beginning. And in the rest of the block processing, the seed doesn't appear. So this means that block processing is actually independent of the seed. And when this while loop is done, there's the finalization phase. And if you have a closer look at this, you will notice right away that if we keep ourselves to 8-byte line data, then none of those things will actually be applied to your hash. And this only makes our task of finding collisions easier. So the main strategy of our attack borrows some principle from differential cryptanalysis. And this is the high-level strategy that we used. So we introduce a difference in the state of H by using the message blocks. And we will cancel this difference right away by introducing another second difference. So let's have a look at how this would work in the code. So imagine we're in our first round of this while loop, and we get the first block of the message. We inject a difference there, and we will choose it in a way so that after the processing of k will have a difference of exactly 0x80 and all zeros. And then h gets multiplied by this magic constant that doesn't do anything, but once h is being XORed with k, this means that in h we have also this difference of 0x80, and the difference in relation to the original values. So if we had a message, let's say A, then this message here is slightly modified and has all those differences. Now, if we enter the second round, we will again introduce a difference in the second message block, and we will choose it in a way so that, again, after processing, we have this difference of 0x80. And as you can remember, that H in the first round already had this difference of 0x80. And what happens now if we XOR both together is we will cancel out the difference. And so we will get the exact same hash value. And we get the collision there. So we don't have to restrict ourselves to just one message pair. We can actually choose n pairs, chain them together, and we will get the same hash value. And the nice thing is that we can reorder them. The order doesn't matter. And so we have 2 to the n combinations if we reorder those pairs. And if we take a string of 16 n bytes length, 16 because we have 64-bit message blocks, and we have a pair, so that's 16 bytes there. And this means that 16 n bytes gives us 2 to the n collisions. So in all of this, I never talked about the seed. So this means even if you have a perfectly random seed, this will still work. And therefore, the approach is universal. And the exact same principle can be used for murmur-hash 3. Murmur-hash 3 is actually pretty similar. It's slightly more complicated, but it works too. So what does this mean? This means that anybody who's using murmur-hash right now is still vulnerable to this hash denial of service attack. And yeah, we got the theory, so let's apply this in practice now. Okay, we got a recipe, and all we need to do is bake a cake. So let's start to look, where could we actually apply this? And yeah, this is a short list, so you don't have to go through all of this. I think the question is rather, where aren't hashes used? So every real-world application has them somewhere. And yeah, they even appear in places where you don't actually think about hashing. So Pascal Junot recently found this nice attack on BTRFS. And you could ask me right away, so if they're that bad, why don't we use something else? And Dan already talked about this. I think it's that this dream of constant time insertion and access is pretty attractive. So let's have a look. Where can we use this? So we wanted to have a high-profile target. I mean, we could try a lot of things, but we chose web applications because they're pretty popular. And so last year, people, Clink and Welder, they attacked Rails, and since I'm involved in Ruby development, I love Ruby, I love Rails, this was the natural candidate to look for. So to do this, I would first have to attack murmurhash in Ruby itself, and since I had the recipe, I just wrote some Ruby code to apply this recipe that was pretty much straightforward, and let me show you. Let's need your help.
1, 2, 3, 4, 5. Okay, there you go.
Okay, thanks. All right, so I wrote this script here, and if I execute it, what you will notice on the left, we have different strings, but on the right, we have the exact same hash value. And if I run it again, we get exact same hash value, but different. And this is the randomization working there, because murmurhash is randomized. So if you try those values at home, you will get different values, but they will all be the same, and that's all we're looking for. Okay, so it worked in Ruby. Okay. Okay, so now that it's working, I should just be able to take this code and apply it in Rails, right? No. Yeah, that was pretty frustrating. What did happen? So I got encoding errors, and this is the part of the code that handles request parameters in Rails. This is happening in rec, if somebody knows it. And what happens here is the key value pairs are split, and then since we use form encoding, they need to be unescaped. So it could be that there are some form encoded things with % and hex characters. And this is what happened. You can see it raises an error if the data doesn't comply with this regular expression. Looks a little bit complicated, and what it actually does is it catches invalid % encoding. So if you have 2 consecutive % or non-hex characters, it will throw this error. So I paid attention to not produce such things anymore, but then the next line caught me. So what does normalized params do? Again, one of those beautiful regular expressions. And yeah, what it does is it just flattens. If you have nested empty bracket parameters, it will flatten them down to a single pair of brackets. And that's why it's normalizing the data. And it was actually pretty complicated to try to deterministically create parameters that would pass both of those checks. And so I'm lazy and I got bored, so what I did was just brute forcing my way through. So I created random values and hoped that some of them would pass, and those I would keep, the others I would just discard. And it worked pretty fine. So I was happy. Now it should actually work, right? But that's the experience that I made. So I was so eager to find collisions that I didn't care to read the first line. I mean, key space constrained params. That should have rang a bell, but it didn't somehow. Let's look at what this does. It's an extension of the Ruby hash class, and what it does is if you insert a key, it will keep track of the overall size of any key that has been inserted so far. And once it hits a fixed limit, it will just reject any more keys. And yeah, that's a pretty nice idea. I think every web application should be doing this. And yeah, respect, but unfortunately it totally screwed my attack. So yeah, I was depressed. I got this far, but come on, Rails can't be doing this to me. And I remembered, yeah, well, hashes are used anywhere, so big deal if form encoded data doesn't work. So I will just go on to the next target. So let's try JSON. And yeah, I hit exactly the same problems, encoding problems, and I fixed them exactly the same way by brute forcing. And yeah, to make things, speed things up, here's what happened. Okay, so I have this very stupid Rails application that basically does nothing here. You can't see it, it's running, but and yeah, I brute forced this data here. This is just to show you what normally would happen. So these values that I send to Rails actually don't do anything. So as you can see, this is, now let's go back to see what Rails told us. Rails told us that, oops. So can you see it? Exceeded available parameter key space. That's the clever little bastard at work. So, okay, this is what normally happens, but now let's try the JSON data. Okay. So if you think about it, can you see it? It's 4,000. So it's pretty amazing. It's just 4,096 keys, and it already takes 7 seconds. So if you take a realistic number, then this will totally, yeah, you get timeout errors. Okay, Rails is done. And one thing we should have immediately learned from this experience is that trying to fix every little place where hashes appear, this just won't work. So I think there are just way too many places where hashes occur. And imagine all the ugly pieces of code that you would have to add, and they don't have anything to do with the business logic. And even if we tried hard, I think somebody would overlook something somewhere, and there will always be a loophole to be found. So I think the only chance that we got is to fix this where it actually happens, and this is by fixing the hash function of the programming language. So since I'm involved with Ruby development, I didn't want this to become a Ruby thing, and people start talking, yeah, this is a Ruby problem, so Ruby is slow anyways, or and this is why I thought we need another target. We need something that's used in the enterprise. And we haven't talked about Java yet. Okay, so with everything that I learned from Ruby, this should just be child's play. And I would simply apply the recipe. I would prepare my byte array strings exactly the same way that I did it for Ruby, create strings from it, put it in a hash table, and it didn't work. But why? So I started looking into Java source code, and in the string constructor, as you can see here, every time this is associated with a character set, and this character set will try to decode the stuff that I feed it. And whatever I feed it, it will totally mess with my bytes, and so the attack wouldn't work. And I couldn't find a way to circumvent this easily. And I was a bit depressed, because I thought, okay, Ruby is affected, but Java is not? Come on. Something needs to happen. And then I had an epiphany. There's another constructor that takes character array. So let's look what this one does. And no decoding. So the rest was easy. I would simply take a character array, process 2 bytes at a time, and write the result into one character. Because character in Java is 16-bit wide, so I can simply process 2 bytes at a time and simulate operations on bytes. And yeah, let's see if this worked. So it's using Oracle JDK, the newest update, I guess. So in the first example, this is non-colliding elements. It returns right away. And if you use colliding elements, then it takes 7 seconds. Okay, so good news, the enterprise is affected too. Okay, we reported our findings, first to the Java people, then to the Ruby people. And an OCERT advisory was created, CVEs were assigned. And if you want to find out more about the attack, especially how those differences, D1 and D2, I didn't actually talk about how to choose them. If you want to know more about this, and if you can bear to read it, it's on my blog. And if you want to play with the proof of concept code, it's on my GitHub account. So Schadcode is if you apply Schadenfreude to hash functions. Have fun with that. And let's see what the reactions were. So let's see what the Java people did. And the response was, I first had an audio effect here. That was the sound of Java not giving a fuck. And so they didn't do much. And let's see what the Ruby people did. They actually fixed it. So first in C Ruby, then in J Ruby, and finally in Rubinius. And this is why you should use Ruby. So at this point, I really want to thank you guys if you watch. They did a fantastic job. They already did last year after last year's attack. They were the first ones to fix it last year. They're the first ones to fix it this year. And it's still an open issue in Java. So thanks, guys. Now, I said they fixed it, but I didn't tell you what the fix was. So is there a way to really fix this? And this is what Jean-Philippe is going to tell you about. Thanks.
Okay. Well, I'll try. So you know that murmur hash is not the best hash function in the world, so the first thing to do is not using murmur hash, be it 2, 3, or 4, or 5 anyway. You might have heard about something called city hash. Do you know city hash? Yeah, okay. City hash is something designed by and for Google, and they say on their official page that it was developed starting in 2010, and they use variants of city hash 64 mainly in hash tables such as this C++ function. So as far as I know, they only use it internally. I don't know of any third-party application that uses it. But well, it's designed by Google, so it's probably more secure than murmur hash. Well, actually not. It's much weaker in the sense that for the same size of message, you can find much more collisions. And it's the same property of universal multi-collisions. You find a bunch of strings, and they will collide regardless of the seed that you choose. Okay, and one additional property is that it's quite easier to find well-formatted strings like UTF-8 or ASCII strings. So you see, I have an example of only ASCII symbols, and you see that they are all to the same value. Okay, so let's not use the hash. What about Python's hash? So last year they were vulnerable to the same hash flooding vulnerability, and they added a randomization function. So if you call Python -R, they use a random scene in this function. So is it secure? Well, it's maybe a bit better than city hash and murmur hash, but it's still not really that good, because here we wrote a simple script, maybe a couple of lines of Python, and we recovered the value called py-hash-secret. So this is actually the seed, the secret value that is used by Python. And why we can do that is because they designed the hash function in quite a non-optimal way. They actually use the value that we hash as the key of a block cipher, and this tiny block cipher is encrypting the secret value. And the hash value that you get is the ciphertext. But you know the key, you know the value that you're hashing. So you just have to reverse this block cipher to get the original value. And well, but it's not really good because, as you see, there's two different values here, the first line and the second line, because there are actually two equivalent seeds for each seed. Okay. So it doesn't directly give you a way to perform hash flooding, but this can be done by time array trade-offs. This is the same function in Python 2 and Python 3. So, by the way, this is an optional randomization. You need to explicitly add the option. So we have this instantaneous key recovery, and multi-collisions can be found by pre-computing large tables, because the internal state is only 32 bits. So it's quite easy to do multi-collisions and hash flooding in Python. Okay, so we should not use murmurhash, cityhash, or Python's hash. There's something called Marvin32 hash. So has anyone heard about a function called Marvin hash? Yeah, probably not. This is defined in the .NET framework in CLR.dll. This has been recently reverse engineered, and it doesn't look that bad, but we're looking at it, and well, we'll let you know if we find something. But this again doesn't seem to have been designed with security in mind. It's extremely simple. So what about using something designed to be secure and fast? So let me introduce SIP-hash. The SIP-hash is a new cryptographic algorithm, what we call a PRF, which is essentially a keyed hash function. So a hash function with a key, a secret key. This is a project that we started after the talk of last year at CCC, because we felt that, well, this kind of thing was needed. And we started with really rigorous security requirements that we said, okay, to avoid this hash flooding, we just didn't look at a heuristical pseudo-randomness definition. We say this has to be this kind of cryptographic object, namely a PRF, which is a pseudo-random function. This is a well-defined object in the sense that this should be indistinguishable from an ID. Well, I won't go into details. The other requirement is that it had to be as fast, well, almost as fast as the weak hashes. So it was quite challenging because on the one hand, we want to be more secure and as fast. And we also wanted it to be usable by cryptographers as a message authentication code, or PRF. So Mac, you probably know HMAC. HMAC is not extremely fast. PRFs are used everywhere. For example, you may know PBKDF2, the password hashing scheme. It uses a PRF. So that's actual research. We wrote a research paper. It was peer-reviewed, accepted at DIAC and Indocrypt more recently. So I will try to present to you how SIP-hash is working. We try to make it simple, and maybe you have implemented AES and you know that AES is a very nice cipher, but you need to know about polynomials and finite fields, this kind of complicated objects. So we try to make it as simple and as easy to understand as possible. So we just use a simple state composed of 4 64-bit words, V0, V1, V2, and V3. We have a 128-bit key, key 0, key 1. And we start by initializing the state to K0 XOR this value, K1 XOR this value, K0, and K1. So does it look random? Well, it's not really random. It's some sort of randomly generated bytes. It doesn't matter much. We just want something that is not the same values, but it's easy to remember. So then you have an input of arbitrary length. You parse it as a sequence of words, of 64-bit words. And you first XOR M0 to V3. You perform C iterations of a function called SIP-round. And then you take the same message block M0 and you XOR it to V0. You do the same for M1, M2, and so on and so forth. So how does SIP-round look like? It's just a simple sequence of operations from the left side to the right side. So you see we're just doing XORs, integer additions, the squares, and word rotations. So we do 13, 17, 16, and 21 because it's, well, it satisfied our criteria of security of diffusion, and the 32-bit rotation, it adds more security, and it's easy to implement on 32-bit machines. And the finalization is just XORing the byte 0xFF, doing d iterations of SIP round, and XORing the 4 state words together and returning the 64-bit value. So quite simple. So we have this C and D value that are not fixed. We propose SIP hash to 4. So for each message word, you make 2 rounds of SIP rounds, and you finish with 4 rounds of SIP round. So we make the same function at each round. You just have to implement SIP round and to iterate it. Okay. So we propose to use SIP hash to 4 for hash tables, for example, because it's extremely fast. We also have a conservative proposal SIP hash 4.8, which is obviously twice slower than SIP hash 2.4. Cryptanalysts may want to break SIP hash 1.0, SIP hash 2.0, SIP hash 1.1, 2.1, and so on. We don't make claims of security for those weaker variants. There may be some distinguishing attack, or I don't know. But we recommend at least SIP hash 2.4. Our security claims, so it's approximately 120 bits of security to find the key. Another way to attack SIP hash is to not recover the key, but to recover the state, because this can also be used to forge a hash value. A special type of forgery attack is done by finding collision in the internal state. This requires approximately 2 to the 128 values. And if you try 2 to the s values, then you will make a successful forgery with this probability. Okay. So I want to enter into the details of cryptanalysis because it tends to be a bit boring. But just to know that we really studied it with using the state-of-the-art tools, because most of the attacks today are differential cryptanalysis, and this is about introducing a difference in the value and predicting its propagation through the iterations of rounds. So just to show you a simple example, so here we introduce a difference of 1 bit. And after 2 rounds, we have a Hamming weight of 13, 14. And after 4 rounds, this is as high as 100. So we really try to optimize the diffusion, which means the number of differences given one single differences in the input. And the second criteria is what is sometimes called confusion, which essentially means the mathematical properties of the equations. And we do this by having combination of integer additions and XOR. And this guarantees that algebraic attacks that you may have heard in the previous talk will not work against SIP hash. Now how fast it is. So on this laptop, it's a quite old AMD Athlon 2 Neo CPU clocked at 1.6 gigahertz. If you only hash 8-byte values, but many of them, this will make, in average, 123 cycles per 8-byte message, which means approximately 15 cycles per byte. And this hash is at a rate of about 100 maybe bytes per second. So you see the more bytes per message you hash, the faster the hashing rate, because the overhead of initialization and finalization is reduced. And if you hash very long messages, like 1 megabyte messages, it's as fast as about 1.44 cycles per byte, which means 1 gigabyte per second. So it's quite fast. But is it as fast as murmur hash or the weak hashes? Oops. Okay. So it's the red line here is SIP hash, and the green line is CD hash, and the blue one is something called spooky hash, which really looks like a murmur hash and CD hash. So you see that we are a little bit slower than those weak hashes, but we're much, much faster than another weak hash, which is MD5. You have heard about it. And yeah, I don't think it's a good idea to directly compare SIP hash to MD5, but actually it's much, much faster. Okay. So what we call a proof of simplicity, we were extremely pleased to see that just 1 week after publishing the specs, there were a number of third-party implementations that we did not explicitly ask in C#, in C, Cryptol, and other languages I had never heard about before. If you use Lisp or Ruby, if you heard about Ruby, no, okay. So I encourage you to use to zip hash, and since we published it, a couple of people adopted it. OpenDNS in all its DNS cache instances is now using zip hash 2.4. CRuby, Rubinius use it for hash tables. Perl, Rust of Mozilla Foundation is using zip hash as well, and it will soon be in the Haskell platform. Okay. So you just have to remember three things from this presentation. So this hashflooding DOS, it works by forcing the worst-case behavior of the application so that it be too slow to perform all the operations you want it to do. We found that Java by OpenJDK and Oracle are vulnerable. The three main Ruby implementations as well, because they use murmur hash 2 and 3. You shouldn't switch to CD hash or Python's hash. And we propose zip hash to be both secure and fast. And since we published it, we haven't heard about any attack. I'm not aware of people who try to break it. I know there's a university in Austria that is proposing a project to their students, but I don't know if they did anything concrete yet. So if you want to learn more about this, we have a website where you can find the paper, all our code, the proof of concept code, implementations of zip hash, all the slides, and we'll soon publish a paper with all the details of the attack on CD hash, murmur hash, and Python hash, and maybe more. So thank you very much.
Thank you very much for your presentation. If you have any questions, please line up here behind microphone 1 and microphone 2. We have about 11 minutes left for questions, if you have any.
Hi. Oh, das war schon.
Okay, there is a question from microphone 1.
The extraction, oh, wait a minute, okay?
Yeah. Please quiet down so we can hear the questions.
Is there a token sensory?
Okay, so maybe we can turn up microphone 1 a bit and you can ask your question.
Okay. The extraction of the hashing secret you've shown for Python, it is only an attack vector if I have a library or something in Python where I can actually extract the hashing results, right? It's not feasible if I have a web framework, say Django, where I put in values that I know will be hashed, right?
Well, we haven't spent much time trying to put this in practice, but to do it, you need to have access to the hash values of at least 2 chosen messages. And we don't know how feasible it is in concrete web applications, for example, because since you need to have access to the internal hash value.
Okay, thank you.
Okay, microphone 2, please.
Hi, I also have a question to speaker 2. Do you have some numbers, how many strings you had to sort out to find collisions where you have 2 strings having the same hash? So is it 1 in 3 or 1 in 100 or 1 in 1000?
I didn't really count the relative frequency there, but I think it was about between 1 in 500 and 1 in 1000. So computing 2 to the 16 matching keys took about, at my faster new laptop it finishes immediately. So I think it's reasonable to go as high as 2 to the 20, 2 to the 25.
So you think you can generate enough collisions to crash any web applications?
Yes, certainly.
All right, thanks.
Okay, thank you for your question. We have a lot more questions from microphone 1. Please go ahead.
Could you repeat what was wrong with the Python design, what they did there with using the input as the key? I missed that. Could you explain it better?
Essentially, what they make the hash, instead of behaving like a random function, it behaves like a simple permutation, an invertible operation. So if you get the output, it's easy to retrieve the input. Like, you can imagine this like a yes if the key is known. So if you know the ciphertext, you can easily get back to the plaintext.
Okay, a question from microphone 2, please.
Yes, hi, thanks for the talk. Is there any work to tie back an attack back to the user and cut off the connection? Like if a user is providing too many inputs that are invalid for the hash?
There have been several such efforts. There are quite a few applications which are trying to, for example, count the number of collisions they encounter and stop processing if that number grows beyond what it should be. The problem with that is that you have to check every single use of your hash tables to see if you're encountering that kind of problem. Some applications you can get away with saying, okay, we're not going to handle more than, say, 1 kilobyte of input. And within 1 kilobyte, you can't do a lot of damage with these kinds of attacks. But most applications can't enforce that kind of limit. So for typical applications, the chance of somebody getting that kind of defense right is negligible. Whereas if somebody really fixes the problem in the hash function itself, then it's gone. I mean, the problem's gone for everybody. So there have been some efforts along those lines, but it would be awfully surprising if anybody actually achieved a secure system in that way.
Thanks.
And 2 questions from IRC.
Thank you very much. First question from the IRC channel is, how was the hash prediction prevented? Through a host-specific secret salt or any other method to avoid the issue with modulo 20?
Could you please repeat the question?
DJB, you have presented the generic approach, which could be applicable to even SHA-3 with a modulo 2 to the power of 20 approach when you can predict the hashes in advance. How is it prevented in the current implementations?
Okay, so if you know what the hash function is as the attacker, then you can go ahead and try a bunch of strings yourself on your own computer and look for examples of strings that collide or produce a particular output. But if you don't know what the hash function is because it's strongly seeded by some random secret number that the hash application is generating, then suddenly you have no way to tell what the hash function is aside from talking to the server. And then if you talk to the server and the server is leaking information which lets you figure out what the seed is, then you're still in trouble. So just because you have some randomization doesn't solve the problem. But at least that's the basic starting point, is a hash function that has some random secret coming from, say, dev-urandom that the attacker doesn't know.
Second question.
And a second question is from a frightened user. If he's not a mathematician, how should I use hashes the right way if he needs to use them in a web app?
Yeah, well, I think the easy answer is use ziphash. I'm not sure if the question was more going in one direction from that, but ziphash is meant to be the easy answer of just get some random key from, say, dev-urandom, and then use ziphash, and then you don't have to worry about what's going to happen with your hash table.
Okay, so you've been waiting. Yeah, please.
I have 2 questions, but we'll see. So the first one is, how do you prevent them against the algebraic attacks? It was very quickly stepped over, and I wasn't really. I'm just interested.
Well, algebraic attacks only work if you have a strong mathematical structure in the cipher. And due to the specific construction of zip hash, the combination of add, XOR, rotation, this completely breaks down any exploitable algebraic structure.
Okay, we'll see.
I don't know if Mr. Courtois is here, but maybe he can confirm.
Okay. And the second question was, so there was this competition with SHA-3 and everything, and it's meant to be fast enough. So why don't you just use SHA-3 and then prepend the random string, you know, as you would basically randomizing the system?
So to give you, sorry if SHA-3 is approximately 10 times slower than zip-hash.
But then how can zip-hash be so strong? I mean, there must be some kind of relation between strength and...
Well, I'm not the one who chose SHA-3. I wouldn't have picked this one for obvious reasons. More seriously, SHA-3 is a general purpose hash function where zip-hash was optimized for short inputs. It doesn't have the same level of security. SHA-3 supports security up to 256 bits, whereas zip-hash is limited to 128 bits with different security notions.
Okay. Thanks.
Thank you. I think there are more questions in line 1. Please go ahead.
Yeah, I think that Jean-Philippe knows about Blake for good reason.
What is this?
Blake.
Never heard about it.
No, this is not yours?
Yeah.
So why did you need zip-hash if you had another one that was finalist for the SHA-3?
Again, because we designed Blake to be good in various platforms, be it software or hardware, and to satisfy the requirements set by NIST. But here we have completely different requirements, and even though Blake is quite fast, it's maybe approximately 3 or 4 times slower than zip-hash, and it's not as fast as MD5. But I would like to take the opportunity to advertise a new hash function called Blake 2, which is a much better version of Blake. You can go to https://blake2.net, and we have a nice website with very good code and specification. Sorry for the advertisement.
Okay, we have time for maybe 1 or 2 more questions. Are there any more questions? Okay, then thank you very much. Yeah.